Okay, good morning. I'll try to live up to the introductions of this being a highlight of people's calendars. And I'll try to keep the propulsion joke to the absolute minimum and stick to the main thrust of my thesis. So, pause for laughter. I'm Thomas Hall. I'm under Vias Lapas, the head of the propulsion division at Surrey Space Centre. And I will be talking to you about the development of a small-scale Helicon double-layer thruster. Quick overview, just to let you know how long you're going to be looking at this. Some propulsion basics, just to get everyone up to speed on. What is propulsion, so you can sort of follow everything. Then moving on to electric propulsion, and why this is better. I think standing underneath speakers is a bad idea. It's unfortunate. We've got some problems. Okay, there we go. So yes, electric propulsion, what that is. And how it's different from chemical propulsion, which is the sort of standard mode. The hardware of the thruster that I'll be working on, some of the principles of operation, how the HDLT, as it's known around the Space Centre, works, some of the current work, and then just wrapping it up. Okay, so propulsion basics. This is the granddaddy of propulsion equations, really. And it basically states that to get a change in velocity of a space vehicle, you require an expulsion of some amount of mass. So you'll have your initial mass, and you'll chuck some mass out, and then you'll have a final mass. So this ratio, nice and high to get lots of delta V. And this is the speed at which your propellant is expelled. So to get a large delta V, you can have a high change in mass, or you can have a high exhaust velocity, or a combination of both. So an increase in either of these two guys will get you a nice large change in velocity of your vehicle. Bear this in mind. So another way we can say put a figure of merit to this, put a number to it, is specific impulse. I promise you these are only two equations in the entire presentation. So specific impulse is a figure of merit, kind of like miles per gallon in a car. So it's a measure of fuel efficiency. It's literally just the amount of thrust you can produce for a given rate of propellant usage at sea level. We use at sea level because then you can compare all thrust technologies, propulsion technologies across the board. So again, bear this in mind. So a typical chemical propulsion technology. Here we've got a hydrazine decomposition thruster from Astrium. Very, very simple. You've got a fuel tank of hydrazine, which is passed over a catalyst, which then decomposes, creating hot gases. These hot gases are expelled out back, and you get thrust. Now, possible problems with this is that all the energy supplied to your exhaust gas comes from the molecular bonds in your propellant. Now, this is a limitation because you can only get so much energy, chemical potential energy in your fuel. So, you get an exhaust velocity which is, moderately high, not particularly high, generally limited to about maybe 11 kilometers per second, but comes back a bit later on. But the problem with this is that you have to carry a large amount of fuel with you, which then displaces what you want to be putting on your satellite, like communication, scientific payload, this sort of thing. So to summarise, low exhaust velocities, I've got my numbers on over there, 3 to 5 kilometers per second. High mass flows results in a low specific impulse. You can get large thrust from this though, so everything has its place. So with your high thrusts, you can launch something into space from the ground, but if you're looking at a long mission, then you're going to run out of propellant pretty quickly, which is not useful. So if you want something that you're going to be using in space that you can use for a long time, you need a high specific impulse. So a way we can do this is by decoupling the energy you can supply to your gas from the fuel itself. So you're not relying on molecular chemical potential energy to get your exhaust velocity nice and high. So this is just a definition posed by a guy back in 1968. The acceleration of gases or plasmas for the purpose of producing propulsive thrust by electrocuting electric body forces and or magnetic body forces. It's just a nice way of summarizing it all up. But by separating the chemical potential energy you have in your fuel from your energy-giving mechanism, we can get very high exhaust velocities. I'll show you how this is done. So, this is just summarizing, you can get high specific impulses from your high exhaust velocities, and you can reduce significantly the amount of propellant you take on board with you. So you can make way for your communications payloads, your scientific payloads, all this sort of stuff. So some typical numbers, just to put something behind this. So Ariane 5 stage 0, obviously huge thrust, millions of newtons. Specific impulse, it's pretty lousy, 275. And if we go down here, the hydrogen thruster that I showed you, this is installed on quite a few small satellites, sub 500 kilograms, 0.5 Newton, moderate specific impulse. And we start getting into the domain of electric propulsion, and we can see that our thrust drops off significantly, but our specific impulse goes through the roof. So we can be very efficient in our usage of the propellant. So if you can imagine you're on an interplanetary trajectory, say to Mars, for example, it may be useful to provide a small but constant thrust to your space vehicle, rather than giving a massive whack and just hoping that you get there on the other end. So if you're relying on your electric propulsion technology to be up there for a very long time, be very efficient in the use of fuel, it needs to be very reliable. So how can we ensure this? Well, it needs to be very simple. Minimum parts, you need to make sure it's robust, that it's not just going to fall apart, melt, whatever, and the whole thing is just very reliable. This can be a problem. Electric propulsion has a, shall we say, a stigma about it since it was introduced back in the day, and they've been typically hallmarked as a complex technology which is vulnerable to failures, and it's been very slow on the uptake in space. Here's a typical example of a very successful engine, in fact, the T5 gridded ion thruster. This has been used on very high-profile missions, such as the Gochi gravity mapper. I'm sure some of you will be familiar with this. But the basic idea is that you create a plasma here, so an ionized gas, and you have some high potential grids, literally just some metal mesh, which you hold at high potential between these two grids. So the charged ions see the potential, roll down it, get accelerated out, and you end up with a mass of positively charged ions here. You can see it's a plume just here. This needs to be neutralized, otherwise you'll end up with these ions sputtering your spacecraft, destroying the space solar panels. You really don't want that. So you inject electrons to neutralize the plume. We can see a problem already. These positively charged ions are going to be hitting up against this grid, they're going to be exchanging charge, they're going to be sputtering it, eroding it. The hollow cathode here, the electron gun, this is another possible failure point. You have to supply propellant to it. Things start getting complicated, and there are possible failure points. These are, however, very highly rated, but if you're looking for the ultimate propulsion technology, then you want to try and make it even simpler, if you can. So enter the Helicon double layer thruster, and my personal baby, the mini HDLT Helicon double layer thruster. This is a scaled down version of a novel propulsion technology that was invented in the Australian National University. My design is targeting small scale, low complexity, low thrust propulsion for small satellites, so sub 500 kilograms. And also, I'm a physicist, my undergraduate, so I kind of have an interest in the physics that goes on inside there as well. So all the engineering is interesting, but it's nice to see what's going on inside there. So onto the good stuff, the hardware. This is just a CAD diagram, just to start off with, just to show you how it all fits together. I'll be showing you some actual photos in a second. So pulling the whole thing apart, these are just solenoid formers made of aluminium. These are solenoids, just copper wire wound. Here we've got a source tube. This is generally made out of quartz or Pyrex. We've got an antenna here, helical antenna, similar, or not dissimilar certainly, to some of the helical antennas I'm sure you guys use. And these are just supports, just to keep the whole thing locked inside here. So again, this is just sort of pulled out, it's all squashed together in reality, and I'll just be showing you the pictures now. So these are the solenoid formers for the mini version. Again, very, very simple. We just got some wound solenoids here. This is just all aluminium. And inside there, we've got the source tube. Our one's made out of Pyrex. This is about 5 centimeters in diameter, so we're pretty skinny, about 17 centimeters long. And then wrapped around this, we've got an antenna. This is white. It's actually made out of copper. We've coated this in boron nitride spray, just a very high temperature resistant spray. We found that, I guess, certain inadequacies in our initial experimental design caused the antenna to actually be deposited onto the source tube, leading to some people suggesting that, do we really need an antenna? Surely we can just spotter it all onto the source tube itself and just connect it all up. Unfortunately, we can't do this. So we tried to avoid this initially just by coating it in boron nitride. So, on to how this thing works. Argon propellant is what we're using, so a completely inert gas, very easy to store, also very cheap, hence why we're using it for our initial investigations. We pass propellant through the source tube, just through this little hole in the back here. We just have a little tube that kind of goes up its backside, and we pass propellant through it. We use radio frequency power, 13.56 megahertz. And the antenna type itself is a Boswell type antenna. This was because it was created by a fellow named Rod Boswell, a guru in the Plasma Physics Society. And the antenna is designed to match a wave, which, on reflection, I suppose many of you will be familiar with. It's the cylindrically confined version of a Whistler wave. This was picked up or initially discovered by, I believe, soldiers in the First or Second World War. They used to lay long lines for communications, and they found that when they were listening in for enemy communications, they heard these whistling tones from Earth, they called it. They kind of sounded like pew, pew. They're called whistlers, and these are Whistler waves, which travelled around the Earth's magnetic field. The Helican wave is basically the cylindrically confined version of this. So when you take a Whistler wave and try to excite it in a plasma, but you confine it, you end up with a Helican wave. And this can be used to very sharply increase the density of your plasma, because it provides a strong coupling mode. So rather than just pumping power into antenna, hoping that you're oscillating electrons and smashing atoms around, you can couple into a wave mode. And this allows you to deliver energy very efficiently to the plasma. And just to give you an idea of how efficiently. So the W, H and E are kind of counterintuitive, but it doesn't really matter at this point. We've got a capacitive mode. You can imagine just a pair of capacitor plates, and you pass an electric field across them. The electric field which is across the two plates will accelerate electrons from one side to the other. This acceleration of electrons will bombard the atoms, causing ionization. It's a very simple capacitor plasma. You have an inductive mode. This is a little more complex, but again, if you look at the power ranges here, if you increase your power, you're not getting an awful lot of density increase along the side here for the inductive mode or the capacitive mode. When you get to this Helican mode, you increase the power a tiny little bit, you get a very large, couple of order of magnitude, change in the density of your plasma. Now, if you think back to the ion thruster that I showed you earlier on, if you're looking to accelerate ions using grids, then you need to make sure you've got lots and lots of ions. And the more efficiently you can create these ions, all the better. So by using this Helican mode, we're hoping to really efficiently create lots of ions. Plasma densities, for those of you in the know, these are pretty high plasma densities, and you can get close to 100% ionization. So all of your propellant can be ionized and can be used to well, can be accelerated, rather than having neutrals flying around and just basically getting in the way and not being accelerated. Okay, so talking of acceleration, if we're doing away with grids, we need something better. The HDLT uses a naturally occurring plasma structure known as a current-free double layer. This plasma structure has been touted as responsible for a range of natural phenomena, from the aurora borealis, I'm sure you're familiar with, and coronal mass ejections, solar flares. The current-free double layer is said to form at the interface between two different plasmas. So here we've got say the solar wind coming in from the sun, being incident on the ionosphere, causing a double layer. I'll go into in a minute why this happens. And here we have, the sun has various layers of plasma at its surface, and the double layer forms and accelerates ions up and through the coronal mass ejection area. So what is the double layer really? It's just a potential, just an electric field which forms spontaneously. And the clue's in the name, current-free double layer. This doesn't need to have any power input specifically to generate the potential. So rather, with the potential grids, you have to connect it up to a battery or whatever, you know, to get your potential drop. This is spontaneously forming. So just a little bit of plasma physics here for you. If you imagine you've got, it might be easier to come on this side actually. Imagine you've got an insulating wall, just a dielectric, so glass, like in our a Pyrex source tube. This is at a zero potential, and this is x, just your distance from the, say, the side of your glass. The plasma sits at a high potential, and this high potential accelerates the ions to the side, to the dielectric. This is actually used in plasma processing, so if you're trying to sputter something, if you're trying to launch ions at a surface, this is a very neat way of doing it. So you get ions accelerated this way, and the electrons tend to bounce off the potential and get reinserted into the plasma. And the strength of this potential is proportional to what's called the electron temperature. Basically how much energy the electrons have as they're whizzing around the plasma. So this is a single layer, or a sheath. This has been around since Langmuir and the original plasma experiments. So how can we use this to accelerate any of our ions into space? Because remember, we've just got a source tube and an open end. We need two different plasmas right next to each other. The plasma has to be able to protect itself from the other plasma at the interface. So if you imagine this is our source tube here, we get a magnetic field set up from these solenoids, and we get it to diverge out the aperture of our source tube. This allows the plasma tends to follow the field lines and reduce the density of the plasma just outside in this region. So you've got a high density plasma here and a slightly lower density plasma here. This is a slightly simplified model for any of those that are really interested in this. So at the interface between them, plasma 1, plasma 2, you end up with two populations of charged species. So we have trapped electrons here, and you end up with trapped ions here. Positive charge, negative charge. You have a potential which forms across this area. And this is typically very thin. The technical definition is the Debye length. This is tens of Debye lengths in length, in width, sorry. So across this potential, you end up with ions being accelerated and free electrons. So in your high density plasma, you'll have electrons which have just about enough energy to overcome this potential, which is quite useful because you have your accelerated ions being chucked at the back from your high density plasma source. You have electrons which will neutralize the ions once they've overcome the potential and once the ions have been accelerated. This double layer has been measured. This is the original device in which the double layer was discovered. Hopefully you can all see this. So just to take you around here, the source tube is in this area here. This is the source tube, it's a plan view, looking down. These are the solenoids, so you can imagine the HDLT being like this and taking a slice down it. And these are solenoids will be coming around in this direction. This is the antenna here, and the double layer is found to form at about this point here, a 25 centimetre mark. And this is just a dispersion chamber, like a vacuum chamber. You can see the change in your potential is about 20 or maybe about 30 volts in this situation. It varies again depending on the energy of your plasma. So this isn't quite the potential drop you'd get for, say, the T6 or T5 ion thrusters, which are typically hundreds of volts. So this is a low thrust technology. We're not going to be getting tens of newtons out of this. So the double layer has been measured at this point and has been shown to exist, and it works. And it works. So, my work. Again, we're scaling this down. I've just finished on the prototype of the mini HDLT. I'm just thinking if you can see that okay. There's a few more photos. The first trick, obviously, is to measure the thrust of this device, because it's all very well saying, oh, we have all this fantastic physics, it's all very beautiful and it works fantastically, but we need to prove that it does. So we've got a thrust balance. We've attached the Helicon double layer thruster, the HDLT, to the thrust balance here. There's a zoomed out version of this. We'll skip to that so you can see what's going on. This table here is attached to the top table by some legs. We've got some flexures here, here, and here. And this top table can move. So we'll have a plasma being created, the plasma plume, in this direction, say, and will cause a change in the motion of the table in this direction. This thing will tend to oscillate just naturally, and then when you create thrust, you'll see the oscillations jump up and then jump down again. You can average across the two lines and measure how much thrust you're getting. We've got a little pin here. It's called a linear voltage displacement transducer, an LVDT. This is just a method through which we measure the thrust of the thruster. So we recently, this is just another picture actually, just in case you didn't quite get the idea the last two times I explained it. The displacement is in this direction, and we can measure it. Just a little bit clearer. Okay, yes, so we recently turned it on, and it worked, which is fantastic, a huge relief. We've got this is the power supplying unit here, just two big long copper rods which supply the RF power to the antenna. You can see it's all rather bright around here. We have the gas feed coming out the back, which you can't see, it's just obscured by lots of light. And the exhaust plume coming out the back here, blasting the hell out of the RFEA, the Retarding Field Energy Analyzer. It's just a device that we use to measure the energy of ions. Obviously, if we're looking for an acceleration mechanism, if we're trying to determine whether the double layer is there or not, we're going to have a population of ions which are at one energy. If those ions have been accelerated, then it will produce a population of ions that are at a higher energy. And we can measure the energy distribution just using this device. This Helicon mode comes with a couple of visual cues. We've not been able to measure directly whether the Helicon mode is there yet. We just don't have the equipment at the moment. But we have found one cue, and this is the change in colour. So the pink mode on one side, this is looking up the back of the thruster, so you can imagine the plume will be coming out towards you. In the pink mode, this is about 400 watts, so quite high powers. We're seeing, it's pretty pink. This is just the first ionization of the argon atoms. So you'll have an electron hopping back on, releasing a photon, and they're all pink. In the Helicon mode, we're seeing very efficient energy coupling to the plasma, and you get the second ionization energy of argon, which is blue. This is quite a nice visual cue to know that you've got it, although it is anecdotal evidence, shall we say. The Helicon mode is supported by a magnetic field, another use for the solenoids. And this kind of follows from the whistle wave propagation, because the Whistler waves will tend to follow the magnetic field lines of the Earth, and this is just a cylindrically confined version of it. So you need a magnetic field to get the whole thing going. So in conclusion, congratulations, you survived. The Mini HDLT it's a novel electrodeless and self-neutralizing propulsion technology. It provides both the acceleration mechanism spontaneously, with no need to apply any extra power to the device to accelerate your ions. The energy of the electrons which are created on the inside of the plasma source tube have a population of electrons which are sufficiently energetic to overcome this potential barrier and will neutralize the plume of the HDLT. We've manufactured our first prototype just recently, fired it up successfully, and at the moment we're just trying to characterize it and see exactly what it can do. We're all quite excited about it, and hopefully I've managed to impart some of this excitement to the present company. And I think I've finished a bit early actually. Thank you very much.
I don't know if we've got any questions. I've got a couple actually. I was just thinking 13.56 megahertz.
Yes.
Is that the same as RFID ASIC tags work on?
I was pretty sure I was going to get a question like this actually. Yes, communications will be interfered with at high powers. This is one of the problems with RF propulsion technologies, and also a problem with a lot of other plasma in general propulsion technologies. Plasmas support lots of instabilities which are very hard to account for. So you generate what looks like a very nice simple plasma, but in fact it'll be very emissive over a very broad spectrum of frequencies. So one answer I've got how to get around this is don't use a thruster when you're communicating. Another one is I was as surprised as this as you are, I suppose. So just thrust when you need to thrust, and then communicate when you need to communicate. If you're on an interplanetary trajectory and you need to communicate all the time to control your spacecraft, this could be a problem, of course. It is going to be a case of choosing the right mission. Again, this is a new technology, something that needs to be...
And I was wondering, what sort of HF amp, how much power are you using for...
So the power input for... Well, the thruster actually, we can start a plasma at about 5 watts. It's very, very unlikely we'll be getting any decent thrust out of it, that kind of energy. Thrust has been measured, say, for around 300 watts, but in terms of results and numbers, we're guarded about giving anything off too soon because it's a very new technology.
I've heard Martin Sweeting's got a very good HF amplifier if you need to use it.
Oh yes, I think I might be missing out on a joke here, I'm not sure.
Sorry, that's my question. If anybody else has any more questions for
Yes,
Tom,
of course, go away, shoot. Yes, sir.
At the beginning you were talking about some slides with ISP on here and comparing it with other types of thrust technologies. Obviously it's early days, but what type of ISP would you anticipate at the end of your work on this type of thruster?
Okay, so there's a couple of ways we can estimate ISP, a couple of ways we can measure it. One of the ways we can measure it is by looking at the ion energy distribution function, which I mentioned earlier on. So by measuring the ion current, so how much, if you can imagine you've got a distribution of ions, you've got a ton of ions which are at one energy, and you've got like a small population of accelerated ions. You can measure this current, you can equate this to the energy which they have, the potential they're being accelerated through, equate this to the like half mv squared, get a speed. This gives you a sort of exit velocity. We have to be guarded about using this, however, for an ISP because we're assuming that all of these are, perfectly aligned in a perfect non-divergent beam. I mean, numbers have been thrown around for between 1,000 and 1,050 ISP, so competitive with modern-day Kaufman type, the ion thruster I showed you earlier on. However, it is very early days, and with a scaled-down version, we're not entirely sure what kind of ISP we are going to get. It's just going to be a case of characterising it. No problem. Yes, sir.
Two things. I am right in saying that your final exhaust isn't ionised, you've neutralised it, haven't you?
Oh, sorry?
The exhaust is neutralised at the end, is it, to stop
Yes, so once you've accelerated all your ions across the double layer potential, there's a small population of electrons on the inside of the source that have high enough energy to overcome the double layer potential. These electrons have been shown to be numerous enough to actually neutralize the plume.
Right, in which case if you include your entire exhaust in a cut-off safe waveguide, it won't radiate a thing. But the other thing is, have you actually, going back to specific impulse, looked at the overall mass efficiency? Because clearly you've got to take your, probably, solar cells and the efficiency of that electrical and RF power system. So how does the mass efficiency, when you include the overheads, compare?
So mass efficiency in terms of like the solenoid formers, the solenoids themselves, fuel
all
tanks.
The power generation to get the power in. relative
Ah,
to that.
right, yes, very good point. Power generation, the RF power supply itself, this is going to form part of my PhD, just as an FYI, I'm in my first year. At the moment, our power supply is, say, yay big. it's pretty hefty. Well, yes, I mean, again, it depends on what kind of energy you're looking to use, you know, whether it's going to be solar cells or, you know, sort of fuel cells, this sort of thing. But yeah, we're looking into a couple of different options for the RF power generation. A couple of guys have been looking at a pulsed mode, and we can get onto a board this big. We found some RF generators that are about this big, which will go up to about 750. But one of the big issues we're encountering at the moment is tuning. I guess as with radios, when you have a plasma, you'll have your antenna, and this will be, say, you can match the impedance to say 50 ohms on your power supply. Once you've got a plasma inside the antenna, it's like an extra inductance stuck to it. So you have to, literally with capacitors, you're sitting there twiddling knobs, trying to get the impedance matched. And at the moment we've got a big old box, a big old copper box with huge vacuum capacitors. The tuning of it is another issue. So in terms of miniaturizing it all, these are all things which will form a very large part of my PhD, should we say.
Any more questions?
Any at all?
You're using these solenoids, isn't it? You've just got a DC current going through your solenoids.
Yes.
Have you ever thought about modulating that DC current so you might be able to tune it?
So you're suggesting that we say...
Similar to the old technology we used to use when we had old-fashioned colour television sets where you had huge great coils.
Oh, so you're saying, yeah, well, the tuning of the plasma does change considerably when you're applying this DC field and getting like a magnetic field. In terms of modulating the magnetic field, the field is there to support the Helicon mode itself, and you get the most efficient coupling to the Helicon mode when you have a very constant flat magnetic field. The tuning does change when you play around with the magnetic field. In terms of modulating, it may be a bit tricky to couple in efficiently to the mode. The hell, we'll certainly try it.
You could say potentially a lot of energy by doing that.
Maybe we can chat a bit later on about these alternatives.
That's an idea.
Yeah, okay. Yeah, maybe we can give it a go.
Any other questions? Anybody? Okay. Tom, thank you so much for your presentation. It's very much appreciated.
Yeah, thank you for listening. Thank you.